Folks, we'll get started in just a minute as everyone streams in. Just a reminder, just like yesterday, we will be recording this session. So hopefully everyone's cool with that. All right, let's get started. Welcome, welcome. This is the grand finale, the final day of the 2025 Space Apps Challenge, Boston. Regardless of what the thing on the left side might say, it says 6th October 2024. You are not time traveling. We are in 2025, and this is the 5th of October, and this is for the hackathon this year. That's a bit of a typo. So we'll start this programming with an introduction of the judges. We'll talk about a bit of the judging rules. We have 7 exciting teams. I've gone through a bunch of the presentations, and I'm with like everybody else. I'm super excited to hear what you have to present and how the judges ask questions. It's every single year. This is probably the best part of my year because all the submissions you've produced have inspired all of us, and I'm expecting the same this year. We will, once the presentations are done, remember you have 5 minutes to present, 5 minutes for judging, and then the judges will convene in a breakout room, deliberate, and come back with the winning team's announcement, and finally we'll have our closing remarks. All right. So judging rules. First, you have to have by now done the needful. You would have had to register at the Space Apps Challenge website. These are links I put in Discord. You should be registered to the Boston location, which means in the about page of your project, if you look on the right side, it should say Boston. There's at least one submission that was for Universal, so they wouldn't be able to present here. You have to have it for the Boston location. Okay. Second, you need to have submitted using the Google link your presentation and a brief description. That ensures that your presentations make their way to us and we know who you are, we can line you up, and you can present on screen. Okay. If you do need to take over the screen share because you are presenting websites or things like that, you need to you can let us know. But it's really however you want to present, you have 5 minutes to do all of this. Okay. You also, by the end of the day today, 11:59 p.m., you need to go to the Space Apps Challenge website, to your project page, and submit your project. That's the third part. That's important because that will ensure you get your certificate from NASA for participating. Okay, unless that's done, you won't be able to download your certificate of participation. So, awards and eligibility. We have both our local awards. We went through a few of them. Yeah, we went over the local awards yesterday with you. We'll talk a little bit more about it. If you are submitting and you've created your own challenge, you are still eligible for the local awards. There are global awards as well, which is why we all submit this to NASA, as well as the teams submitting here will be selected for submission to the global event by our judges. That's usually the winning team here. In order to do that, you would have had to submit your presentation on the NASA global website, the one that I spoke about earlier. Okay. However, if you have used the create your own challenge part of the story, you're not eligible for global submission. It has to be under one of the existing challenge categories. Okay. So local judging, what do we look for? We went over this yesterday. I'm just going to repeat it. First is impact. What is the potential for impact, both in quantity and quality? Is it a big problem? Is it a small problem? How are you going to, what are you taking on that inspires others? The second is creativity. How creative are you in your approach? Are you trying to use the tried and tested versus a novel concept that has not been attempted before? How does that further the problem solving or the problem solution or the problem and its solution in a way that people did not imagine? Okay. The validity. Is your submission valid? Is it grounded in scientific principles? Is it scientifically feasible? Relevance. Is your solution going to solve the problem that you said it would solve? Does it directly address and solve the whole or part of the solution or part of the problem that's presented that you've been presenting? And the final thing is the storytelling part of the story, which is your ability to present a cohesive story that keeps everybody engaged and is crystal clear and does not cause confusion in people's minds. Okay. Award ceremony. Once you are done presenting, the judges will go into a breakout room, they'll deliberate, pick the first prize, we'll come back and we will nominate you for the first, we will announce the first place. We will also have a second place and our local prizes. However, given that we have 7 teams, one team will be nominated for global judging. Okay. We also have a special AWS award that Samir will select. Samir, he is one of our judges. I introduced him yesterday. He's from AWS, and he will be presenting the AWS award. We also have, as a reminder, some original swag. We do this every year. Our designs are created by our designer, and these make their way to our swag. If you buy them, if you do support the Space Apps Challenge Boston, and the funds go towards making this a great event, a sustainable event every year. All right, now on to our judges. So first we have Christopher Carr. Christopher Carr has been our mentor for Innovative as well as a judge at the NASA Hackathon for many, many years now, ever since its inception in 2014. He is the assistant professor of the Georgia Institute of Technologies, Daniel Guggenheim School of Aerospace Engineering, School of Earth and Atmospheric Sciences. He is an engineer and scientist and with training in aeroastro, electrical engineering, medical physics, and molecular biology. And lots and lots and lots more. If you talk to him, he's probably one of the most interesting people I have met so far. So, Chris, welcome again, and thank you very much for your continued support of the
Chris,
hackathon.
can you give some words to us?
Hi, everyone. It's a pleasure to be here. I'm looking forward to hearing what exciting projects you've come up with, and thrilled to be here for many years. This is an awesome event. Yeah, back to you. Thank you.
Next up, we have Mirza Samnani. Mirza is also a returning judge at ISAC Boston. Mirza is a robotics engineer at NASA JPL. He's been working on various research projects and has led a number of prominent teams in robotics competitions. He's also founded Ignite Labs, which he developed where he developed robots for COVID-19 relief. He was previously at Georgia Tech's Planetary Exploration Lab and has also contributed to the ISS-bound BioX2 payload, amongst other projects. Mirza, would you like to say a few words to the audience?
Yes, there's just a small update to my bio. I am now, this was last year, now I am co-founder and CEO of Iwa Robotics, which is my second venture here, working on renewable energy and some post-disaster mitigation. And happy to be back. I think this is my third year with the Space Apps Boston chapter, and super excited. I've been a participant in other NASA competitions, and now being on the judging side, super excited to see all of y'all's work, and looking forward to what all of y'all have put together today for us.
Awesome. Thank you, Mirza, and congrats on the second startup. Next up, we have Mr. Kenta Tsuchiya. Mr. Tsuchiya is the Deputy Director of the Japan Aerospace Exploration Agency, JAXA's Washington, D.C. office. His responsibilities include conducting research and analysis on the United States space policies, as well as coordinating with other space agencies to advance international collaborations. Mr. Tsuchiya, welcome. Welcome again, and it's an honor to have you here. Would you like to say a few words?
Thank you, everyone. So this is my second time to join this NASA Appli Challenge, and then I'm very looking forward to hear everyone's projects. And then I think yesterday, Council General Takahashi was announced some cooperation between JAXA and NASA, and I'd like to add a few more things about it. So NASA and JAXA has very long history of cooperation from exploration, the satellite, and many things. And also, we engaging with kind of education, cooperation. So this Apple Challenge is one of the, I think this is one of the, best example of that kind of cooperation, educational aspect. So yeah, I'm very happy to be here as one of the JAXA employee. And then, yeah, thank you so much.
Thank you, Tsuchiya-san, and that was very exciting announcement yesterday by the Consul General. So thank you, and thanks for your continued support of the hackathon. And then finally, we have Samir Kenkre. Samir also is a returning judge to ISAC Boston. He leads the corporate VC and innovation group at AWS Startups, which is a group of 1,000 plus former entrepreneurs and investors that help startups succeed from inception to IPO. He and I went together. We were at MIT, and that's where we met. And he is also a graduate of Mumbai University. So Samir, welcome again to the hackathon.
Awesome. Excited to see what you guys are building. This is just my 1-year-old daughter throwing things at me, so apologize for that in advance. Yeah, excited to be here. I've been involved in some capacity or the other since 2014. And looking forward to what you to see what you guys are building this year.
Awesome. Thank you, Samir. And at some point later, you'll be announcing the AWS award. The AWS award would be a consultation with you on their ideas, if I'm not mistaken.
Awesome.
Wonderful. And so, yeah, actually, you want to talk a little bit more about that, Samir? I didn't realize we were doing it right now.
Yeah, no. So, what I'm happy to offer is, some one-on-one time with me, to at least, a couple of the teams that I'm excited about. I'm happy to help you guys, with technology, BD, go-to-market, fundraising, see how you guys, help you develop your idea to whatever that next stage looks like, whether it's, an app on its own or whether it's for the global competition. I'm happy to sit down with you guys and help you sort of take either your presentation or your product to the next level.
Thank you. Thank you very much, Samir. There's usually a long line to get to him. And so this is awesome that you're offering that here and at the hackathon.
Awesome.
3 rounds of judging. So you're here. This is today. You do have the local judging that's happening right now. You heard from the judges. They are going to evaluate you for the criteria we've laid out. In parallel, essentially, as soon as you hit submit at 11:59, your submission will now have gone for global. And so what we would do is to nominate from the submissions here one entry to the global judging. Between late October and mid-November, we have subject matter experts across the various space agencies that participate in this hackathon. It's not just NASA. There are plenty of other space agencies that are part of it. They would deliberate and pick the global finalists. Usually in the middle of November, on November 19, the global organizing team, that's the GO team, organizes the global finalists, and they will announce the global finalists and honorable mentions. The Boston location has a very rich history in being part of the global community and being nominated there. Finally, then you have executive judging that happens between mid-November and January 2025. You have the global leaders, space agency leaders, reviewing the global finalists to announce global winners. Boston, yet again, has a very rich history of being a global winner. And finally, on Jan 16th, the global organizing team will announce these winners, who are essentially 10 winning teams from across the world. And you will be selected for global awards. There are award categories that you would be competing for, right? And so, what are those award categories? There is the best use. This is global, remember. So, best use of science, the best use of data, best use of technology, galactic impact, the best mission concept, the most inspirational, the best storytelling award, the global connection award, art and technology award, and the local impact award. So there are plenty of categories that NASA will judge people on. So these 10 categories, 10 winners, is how you essentially get to be the global winner. But it all starts here. It all starts at this event and the local judging process. All right. Global winners, of course, apart from all the brag rights you get, you do get a global winner certificate. You will be featured on the Space Apps website, definitely in prominent social media. And there is a winner's celebration. You get invited to that. It typically happens in Washington, D.C. at the NASA headquarters there. Right? And now on to the team presentations. We have a lineup. We have a pretty good lineup. And the presentation order, if you can make a note of this for a little bit or take a screenshot, we will call you one by one in line and we'll give you your time to submit or to present. We'll start with AstroTurf Dynamics. Futurescape Navigators is next. Then comes the Exoplaneteers, followed by Pale Blue Dot. And then Heliomesh, Canes, and Team Lumina will take us down back to ground zero. All right. With that, we shall begin. Just remember, once you're done, please, we will send out a survey that we would love for you to fill that out. There is both the Boston survey as well as the Global Satisfaction survey. This really helps us do better. The Boston survey helps us understand how to run the local event better. The ISAC Global Satisfaction survey is to NASA. We don't get access to it, but it is for how to make the overall event better. So we would really love for you to fill that out while the judges are deliberating. We'll flash this slide again. You can take a look at it while that's happening. And with that, I'm going to stop what I'm out and not keep myself between you and the actual presentations. Good luck today. So judges, if you're ready, I can invite Team AstroTurf to come over and present.
Sounds great.
Okay. So we're the team. I'm just going to share my screen because we have the live version and our presentation. Just give me 1 second. Can you see my screen?
Yes.
So whenever you're ready, we would start.
All right. So hello, everybody. We're a high schooler-based team in Italy. And our problem was hunting exoplanets. So the general idea is that we need more funding for NASA to help progress humanity, right? That's why we're here. We based our project off an existing research published in 2022 by Malik et alia, which based their research off of using generic statistics from light waves. And they use the principle of, does this pattern look like a previous planet? And this generates a lot of high false positives. Our approach is to calculate exact transit shape using astrophysical equations and detecting patterns in light curves. The key differences are that it eliminates geometrically impossible planets. Every detection must pass a physical reality check, and it greatly decreases the false positives.
So we asked ourselves, what is the fundamental physical event happening during a problem? The planet is passing off a star and hence creating a drop in the change in flux. We used a lamp and peanut to visualize the change in flux to do the change in movement and hence the area of the peanut on the planet. An important primary information are K and let's say the ratio of the planet's radius to the stars, which determines the maximum depth of the transit, and Z of T, the planet's precise trajectory across the star's face over time using the chord. These two parameters define the entire transit signature. From this, we built a theoretical framework, which is the drop in the star's brightness is directly proportional to the area in the star's surface that is blocked, and we broke the transit into 3 main parts. The first one is when the planet is not overlapping the star at all, as then we can see the change is like it's zero, it's full. The second is when the planet is fully superimposed, the flux drops by a fixed amount of k squared. And the third is the most complex part. During the ingress and egress, where the planet is normally partially covered by the star. And for this partial phase, we derived the exact area of overlap. We calculated the intersection points of the 2 circles we used our cosine to find the areas of the circular segments, and we subtracted the triangular section to get the precise lens-shaped area of overlap. And by joining these three phases together, we obtain a continuous function describing an approximate theoretical model in the change of flux.
So as we were previously saying, the research papers that we read before, such as Malik's ones, were using deep learning models such as CNN, which are supposed to detect overlappments and hence patterns. And from our perspective, this problem is not supposed to be tackled from a pattern approach, but rather from a strictly physical constraining approach. And for this reason, we developed our own PIN, or physical instructional neural network. And we started from this raw data, which is just this change of flux. And we used the NASA's Kepler's and test data set. And from there, we had to fit a function, because we were thinking, since we had designed a function that would describe the change in flux of any planets giving the two radius, if we were able to fit a function in here, we would be able to compare the two areas. And in order to fit the function here, we use what is called the universal approximation theorem. We just use a linear combination of sigmoids, hence a function which just brings a value either from -1 to 1, and hence if there's a change in any of this point, you would go to 1, and when it's constant, you would go to 0. And then once we fit this model, you can see here that we have the fitted model in orange, and from here we would just calculate the interval from where the drop starts and from where it ends, and then we would compare it with the effect deficit that we calculated with the formula before for the same planet that has the same radii and the same radii of the sun. And then from here we would have the two errors. So in this case, for this planet right here, which was the WASP 18b, I think, we had the error was 6.72 times 10 to the 1. And here was 6.29, so they're really close. And then we would just calculate the agreement score, and from the agreement score, as you can see here, we would determine whether or not this was a false positive or an actual exoplanet.
As Alex already said, we only need the part where the transit happens.
I'm sorry for the interruption. 40 seconds left for the presentation.
As Alex already said, we only need the part where the transit happens, also called the dip. Here's the algorithm to detect it. First, we find the absolute lowest point of the graph. It will obviously be in the dip. After that, we only need to find the left and right boundaries, starting from the lowest point and moving to the side until we reach the threshold, which is defined by baseline minus noise value. Then we check if the next 5 points are less than the baseline. If they are, we go further. And finally, we add a minor amount to both sides to be sure that the whole dip is included.
And here are just the results. So we tested over close to 2,000 exoplanets, and we had 100% accuracy, meaning the label was correct. Sorry, and then we developed the website, and from here you can just put the name of the planet and then click explore, and you would get the results from the LLM, which would just calculate the agreement percentage and the overlap of the areas. That's
awesome. Thank you.
Are there questions coming now, or?
Could you give us some guidance on the time we have for questions?
You have 5 minutes.
There we go. 5 minutes. Okay, great. Okay, judges, do you have questions? I have one. Maybe I can start. This is Chris Carr. That was a great presentation. Thank you so much. You really went through a lot there in your project and in your presentation. One question I had is, it seems like it works really well for like a kind of an ideal exoplanet. I'm wondering for effects like an atmosphere or rings or a debris disk or other things, how would you in the future incorporate things that might be a little bit different than what you modeled, but would nevertheless be important findings or discoveries?
So basically, we could implement a density factor in which we take the difference from the density in the center of the planet and subtract the density in the outer radius. So then if the density in the core is the same as the outer one, the factor becomes 0, so the formula stays the same. And if it changes, and let's say there's the atmosphere, the density is going to become lower, the factor is going to actually change the formula and give some more value to it.
Yes, and we were also thinking like to implement a similar thing, or also for the exoplanet where it was a gas or a rocky planet. But the thing is, the data that we received did only have the radius, so we couldn't like actually like implement it right now. But it's something that we were discussing while we were all together defining our function.
Thank you.
Nice.
Hi, this is Samir here. So I'm actually interested in learning a little more about your backgrounds and why did you choose to solve this problem?
So I'm just gonna start from me. So I did the machine learning part, and I've been coding for a long time, but we are all high schoolers, and I've loved machine learning over the past 4 years, and I've developed various models. One of which I'm most proud of is decoding ALS in inner speech. So basically, a model that takes radio signals and maps them to text with the aim to restore ALS. And this is kind of my background, and we just chose this problem because our passions is maths, and we thought that this problem would just be the more fitting one. And if you just guys want to introduce yourselves, you have a bit of your background.
Yeah, so my name is Lubomir. I worked a bit with machine learning before, and I know kind of a bit of physics and math. So this problem was perfectly fitting for me also. That's why we agreed on it.
And personally, I want to study aerospace engineering, and I thought that this was a perfect chance to showcase my skills and actually getting deeper into the field.
Yeah, well, me and Mattia are very interested in aerospace as well as orbital mechanics, and this was just a perfect question to utilize.
Awesome. Thank you so much, guys.
Nice. Thanks.
Any other questions?
Awesome. That was a wonderful presentation, Team AstroTurf Dynamics. Next up is Team Futurescape Navigators. Now, before we get to Futurescape, I just want to announce one thing. I do see a whole bunch of projects or teams on the Space Apps Challenge Boston page. There are around 16 or 17 teams. We did only have 7 submissions on our Google survey. I got contacted by one more team that we are adding. So Bluebergs, you're now added as team number 8. If there are other teams here who haven't submitted on using the Google Forms link we sent you, please do so now so that we can add you and we know that you will be presenting here today. So we have 8 teams now and not 7. Over to you, Futurescape Navigators.
Hello, everybody. We are Team Futurescape Navigators. We are a team of 4 high school students. Shun is interested in soccer, baseball, and baseball stats. I'm Hannah. I'm interested in tennis and piano. Ray is a certified Python programmer along with Shun and I, and also a top soccer player. And finally, Konomi is interested in healthcare and badminton. And for today, we picked the Will It Rain on My Parade challenge, where NASA suggests creating a weather dashboard that finds the likelihood of personalized weather conditions at a location and time using historical NASA Earth data.
So I estimated heat stress in outdoor activities. It is not surprising to experience extremely high temperature and heat stress in urban cities. It's a critical threat for both the tourists and the residents of those cities. Now I'd like to introduce the wet bulb glow temp. It indicates the heat stress on the body in direct sunlight by measuring various factors. WVGT is recommended by major federal, state, and professional agencies. Some of them have announced WVGT-based heat policies. This table below is one of them. It suggests how much and how often you need to rest and get hydrated according to the current WVGT. Next slide, please. As a tourist, I wanted to see what the expected heat stress would look like if I go to Tokyo next summer. Using daily max WVGT data from NASA, I generated histograms and box plots with different history ranges. I found that 5-year historical data gave me the best estimate. With 5-year data, I also compared multiple cities. This violin plot is basically a combination of histograms and box plots. It shows that WVGT distribution in New York City looks like a normal distribution, and Tokyo's has a very high mean and median with long tail. Tokyo's median is higher than those in Taipei and Tunis. The last figure shows cumulative distribution in those cities. In Tokyo, you'd experience the dangerous red or gray heat stress zones at 10% probability. This means if you stay there for 10 days, you'll be in the risky condition on one of the 10 days. In Tunis, Africa, you'd experience the green or less riskier zones at 90% probability.
Hello, everyone. My name is Ray, and my hobby is fishing, which is why I estimated the pleasure and productivity of fishing. To estimate the pleasure part, I considered three factors: daily max air temperature, daily minimum/max temperature difference, and daily total precipitation. For the productivity part, I considered daily water temperature average, maximum/minimum, daily wind speed average, and daily rise above mean sea level. Then I normalized each pleasure factor between 0 and 1. For example, the maximum air temperature is normalized with these equations shown right here. Basically, the normalized temperature is closer to 1 as the temperature gets closer to 23 degrees in Celsius or 73 degrees in Fahrenheit, which is the optimal temperature. It is closer to 0 as the temperature goes farther away from 23 degrees. Next page, please. Then I also quantified the expected fishing result based on the productivity factors. I call it the productive fishing spot index, aka PFSI. It's a numerical number between 0 and 1, which is calculated with this equation shown below. Simply put, PFSI goes closer to 1 as the fishing spot's environmental conditions are closer to the optimum. Since I have dream fishing spots in Australia, I calculated pleasure factors and PFSI for each of the locations and drew this rated chart shown above. Each polygon represents a spot, and a larger polygon means a more favorable spot in the pleasure and productivity of fishing.
Right, and I apologize for the interruption. About 1 minute left.
Estimating weather pain. Studies show that change in barometric pressure can cause headache, fatigue, or joint pain, a condition called meteoropathy. About 30% of the world population experience those symptoms, which cause effect in people quality of life. Therefore, we analyzed barometric pressure using NASA Earth observation data at the end of September. When I have headache, the pressure dropped about 9 hectopascal from September 26 to 27. Since 5 hectopascal from the day before can cause symptoms, this matches my experience. Next, please. Next slide, please. The histogram shows seasonal pressure trend over 25 years in Seattle. The third row shows cumulative distribution function comparing Seattle, Boston, and Miami. As you can see in the graph, in Seattle, summer, only 4% chance of pressure drop by 5 hectopascal. By winter rises for 22%, making symptom more likely. Boston is slightly higher compared to Seattle, and Miami stay below 5% for all season, meaning people there are less likely to get weather-related symptoms. In conclusion, winter have the highest risk of meteoropathy, while summer has the lowest risk due to stable pressure. Next slide.
And we are not only just interested in Earth weather, we're also interested in space weather as well. Space weather refers to solar winds, which is the flow of charged particles from the sun, and they're usually blocked by the geomagnetic field, but sometimes they get into the Earth's atmosphere, causing geomagnetic disturbance and auroras. And geomagnetic disturbance is continuously measured by many agencies, and a well-known metric is AP index. Higher AP means higher disturbance, meaning higher chance of aurora visibility. So using this information, I estimated the future aurora visibility at a particular location and time, and this can help anyone know when and where to go see them. I also use nighttime cloud cover data and the Bortle scale. And for this, I used AP data in 9 solar cycles in the past 90 years and extricated a typical AP change in a solar cycle as well as a median curve after data smoothing and other processing. I also made a visibility table that maps latitude and AP value to a visibility chance. So this median curve and visibility table allowed me to generate the visibility rating for a location's latitude and future date. The rating scheme spans from AAA to C and inspired by financial credit rating. So for example, if you want to go see an aurora in December of 2027, maybe on Christmas, Lapland, Finland has a AAA rating and compared to the BB in Oslo and C in Boston. And that concludes our presentation. Thank you for listening.
Awesome. Thank you very much, Team Futurescape Navigators. Can we have the judges ask questions, please?
So thank you so much for your presentation. And it was amazing that you showed many applying example of the data of the space data. And then I was living near Tokyo last year, and then now it was true very hot in Tokyo, and then that makes sense. You showed the temperature of Tokyo is very high. And it's kind of danger level.
Yeah.
My question is that so Tokyo is hot, so don't go there. It's kind of very sad for me as Japanese. So are there any use case that you can use for you can show the place is good, the Tokyo is good in sense of something or like that?
Are you saying like other are you like other factors or
You can show this is, yeah.
I mean, you can like see like different dates. So for me, I use the date of August 1st to August 21st. That was the date range that I used to collect the data. But if you look at like other days of the year, maybe for other days, it's less hot compared to August 1st to August 21st. So you can compare like different times of year and determine which dates are the best to go to.
That's good.
And you can also go in like different seasons, such as like spring, maybe to see the cherry
Mhm.
blossoms, or winter when it's less hot, obviously.
That's great. Thank you.
I have a question for you. I thought this was amazing, and it was really interesting to see how you came up with different concepts. And so I wanted to ask you, how did you develop your concepts for how to implement these different scores, like the phishing score or like making an Aurora score similar to a credit rating? How did you come up with what was your concept development process?
I'll answer this one. So for a lot of us, we have different interests, and so we kind of zone in on different parts of our lives that are impacted by the weather. So for example, for fishing, Ray wanted to find like the most pleasurable aspects of the weather that would help him enjoy fishing the most because he liked fishing. For Konomi, air pressure was a problem with her because she got headaches when the air pressure was low. So that's why she decided to dig into her own problems. We all decided to look into our own interests, our own problems, and that's kind of how we developed this whole idea of different weather aspects impacting different communities and different problems.
Thank you. So inspired by your own experiences. Awesome.
Yes. Thank you for your question.
All right, and if we could go to the next presentation, it'd be great.
Next up.
Is that showing? Is the screen on there?
We can see you, yes.
Okay. So we are Team Exoplaneteers, and my name is Soham Sahu. My partner is unable to make it, so it's just going to be me. So we made AstroGuard, which is an interactive web tool to explore near-Earth object risks and test deflection strategies. So first of all, as you might have guessed, our challenge was meteor madness. And the problem and motivation behind this is that us humans have existed for 200,000 years, which is a long time. And the dinosaurs have existed for 100 million years, which is a longer time. And they got wiped out by an asteroid in that time. And of course, we have a long time to go before we hit that milestone. But the same thing could happen to us, and we need to be prepared for it. Near-Earth objects can impact Earth, causing tsunamis, earthquakes, or just direct hit to large population centers. And public knowledge of this sort of risk is very limited. And most existing tools just provide data and not really an engaging and easy to understand way to look at it. So the overview of what AstroGuard does is that it explores near-Earth objects in an interactive 3D system, and it simulates local impacts and tests mitigation strategies. And it also has an experimental game mode. For the sake of time, I'll be flying through these so I can explain it more in the demo, but I'll just be listing them off now. So we have a glossary for our features, a live feed of close approaches, an impact explorer, which explores local impact. And then we have 3D visualization. Then we have approach analysis, which shows specific asteroids approach towards the Earth. And then you can modify the orbit with deflection strategies, mitigation strategies like kinetic deflectors. And then as a bonus, we had that experimental game mode, which I'll explain more in detail later. So before getting to future work, I'll show you the actual page. So this is the home page, and first we have the Impact Explorer. So we already have some preset parameters here that we'll be using. And if we select this location and click on Calculate Impacts, it takes a while to run, but eventually. So now it shows you the coastlines that are in danger of being affected by the asteroid if it were to land there. And it shows like a heat map of the seismic danger. If you go down here, you'll see in the details, it'll give you more specific information like the impact energy of 8 megatons of TNT and more, such as atmospheric entry, population affected, and there's a bunch of these. And then scrolling down more, we have the live data, which is from NASA's Center for Near Earth Object Studies. And it shows you the top 6 next approaches that will be happening. So now moving on, we'll go to the actual 3D. Actually, no, before we do that, we'll go to the glossary because I thought for this project, glossary was really important since this is such a little known topic in the general audience, like a general public. So it's important for them to truly understand what's happening. So we have a glossary for them to look through. Now moving on to the 3D interactive. We have just a 3D interactive of all the near Earth objects here. And you can control the time, so you can go forward, you can propagate it up and down, and you can also just directly change time using the slider down here. In the control panel, you can filter out what you see. So if you click on asteroid, you see all the asteroids are gone. If you click on highlight potentially hazardous asteroids, you'll see them in red. So now moving on to the search bar here. If you want to look at a specific asteroid, let's say we want to look at Ganymede's orbit, we click on this. I'll hide this so we can see it better. So now you can see Ganymede's orbit much clearer. And if we click on, let's pick a different one like Bennu.
And sorry for the interruption. About like 50 seconds left.
So we have, let's pick Bennu and we look at its approach analysis. Now here, as I said, it'll show you a close-up of the close approach, as you can see. So it'll show you the distance too, and you can propagate that through using this here. And if you notice closely, you'll see some yellow dots here around the red orbit, the asteroid's orbit. That's actually the uncertainty in the orbit, which we created from the covariance matrix using Monte Carlo simulation. On the right, you have the information, all the information for the asteroid, and we also added tooltips for accessibility. You can disable them with Control Alt I. then you can go to modify, where for the sake of time I'll only show one, but you can I'll modify the orbit. For example, if we do laser ablation, we'll have, I say, that much megawatts, duration of 1,000 days, and 95 efficiency. And let's change it to radial. Then you see the orbit moved slightly, and you can keep on moving it. And here at Impact is the same thing we had the front page, but now instead of it being customizable, it's already preset to the values of the asteroid. And if you calculate it again, which will happen in a second, you'll see the similar thing, but now you have a population density overlay and a fault lines overlay that you can enable. And it has a disaster score, which is based on the population and the energy of impact. Now for the experimental game mode, if you click on the game mode here, it'll pop up a screen where it'll show you time step in days and intervals. So how fast the time moves, and a distance that is safe and a max distance that is too far. So you have to get the missed distance between these two values. So if we start, it'll show you more concisely. So as you can see, the Earth and they're moving at the same time, just in steps. And you can, if we do this, for example, and you apply it, you can check the current missed distance is changing as we're applying more and more kinetic deflectors to it, and it says it's too close. And eventually, once it ends, which I'm probably not going to get this right, but yeah, well, as you can see, that's over deflected and says missed distance is too far. And then for our future, we wanted to add more accessibility, improve visuals, more complex simulations for higher accuracy, and develop the game mode into something more fleshed out than what it is, because it's just experimental right now. But yeah, that's it. Any questions?
That's really awesome. Could you tell us a little bit about your development process of how you develop these different modules? Like what
Of
kinds of
course.
tools did you use, and who did that, and how did you do it?
Yeah, okay. So for the majority, for obviously 3D rendering, we use 3JS, and we had a backend system with fast API that we used to call. And with how the work was divided is that I did most of the backend, like physics-based work, and my friend Karthik did most of the front end 3D rendering and the UI design. That's how we divided it up. And then we started with breaking it into simpler steps, which is what actually helped us develop a lot. Is that, for example, we made a class for any body that simulates an accurate orbit around another body like the sun. So we can use that class over and over again, which really helped us accelerate development. And then the challenge statement itself was well written, so we could pretty much copy it and figure out what we could potentially add next.
Awesome. Thank you. Very impressive. If another judge doesn't have a question, I have another one.
Awesome.
What did you learn from doing this project? Like where did you need to challenge yourself, or what new things did you learn while executing this project?
The most challenging for sure would be the velocity changes, like the mitigation strategies, because honestly, I had no clue how to do them, and I spent a really long time digging into them to figure out how I would model them, how I would show them, and like what they even were. That was definitely the hardest part for this project and the biggest learning point.
Thank you. How did you find your partner, and how did you find working together with one other person on this project?
Well, I've known him for 6 years. He's my friend from school, and I did this last year, and he didn't do it with me last year. But this year we decided to do it together because I was lacking teammates. And he's usually better with the creative side of things and just making things look good. So he's naturally drawn to front end. So he basically made the all front end. And I'm more of a data guy, and I like to work with data and not much with the creative side. So I worked with the back end, and just the fact that I did back end, he did front end really well. It made it really clear to divide the work.
Well, that sounds really fun and great that you both got to do kind of what you enjoy. Thank you.
Right. And I think that's time.
Yeah.
Quickly before we go to the next one, first thing, thank you everyone for submitting. Given the last minute rush, we now have 12 teams, which is pretty awesome. And so we'll spend a little more time here in the presentation because we have quite a few people here. So if you want to take another screenshot of the lineup, that will be great. Team Pale Blue Dot is next. And if you don't see yourself, if you don't see your team in this lineup, please reach out to me. Please fill that Google survey so that we can get you on the list. Thank you. Over to you, Tim.
Yeah.
Pale Blue Dot.
Here we are. Can I share my screen? Thank
Yes,
you.
please.
Perfect. I have a few problems with my connection, but I turn off my screen, my camera. Well,
no problem.
Yeah, let's imagine for a moment. What if 40 years ago, every scientific process had been 100 times faster? What if astronomers had tools capable to analyze dozens of stars in a few minutes or less? Today, we might already know dozens more words beyond our own. Pablo was born from that very vision, making the search for exoplanets no longer limited by human time, without giving up scientific rigor. It's not just a model, it's a new way to think about exoplanets faster, sharper, and stronger. Well, NASA missions, Kepler, K2, and TESS, have observed millions of stars, each one with thousands of brightness measurements searching for a tiny deep light of the shadow of a planet. But among those shadows have thousands of false positive, eclipses, binaries, instrumental noise, or a lot of different variabilities. Today, filtering all that requires human review. Enter team check light curves one by one. But our solutions, we not develop just or train one model or two. We train three. The best of the two different worlds. The machine learning with data and the deep learning with recognize the shapes of these curves. But not just is an idea. It's a viable on the web, right? Or every model brings together two words and really talk physics and artificial intelligence. First, we apply physical transit model based of the article published with NASA, Mandel, and Agel to fit the shape of the transit and check whether the signal make astrophysical sense. Then, convolutional neural network analyze the curve's morphology directly, learning the different shapes, even and an expert A could miss. Finally, we merge these both results and calibrate both outputs. It really means
80% convergence. The result favor false positive, higher convergence, and full, and we can use that on our prototype. Here is a general main dashboard or basic data, and it's available to use for research. It's in a research platform. Right. We built a system, a couple, to analyze thousands of signals in really seconds. Or hybrid classifier, it means record or give us a precision of 96% of precisions, and we can put on them the different data of the
Sorry,
different
I
missions.
apologize for the interruption. About like 50 seconds left.
Yeah, thank you very much.
Thank you.
And we can put the different data on our shadows and give us the classify the light curve and the precision of this classify. If is an possible candidate to be an exoplanet, it's a false positive or it's just a candidate. And more data information for the research. The different training mode, the different pipeline to give us these solutions, the results of this charge of information, and then you can find and download your different reports of your different data that you can find of this page. And right, this is our solution, high performance solutions. And well, let's to continue to the Q&A. We have two repositories and a web repository where you can find our front end or back end, where we put our AI model, these three models, the hybrid model and the performance. The documentation is with a very high level because we can't impact on the two prices, the best use of science and best use of data. We have a very high documentation on these both repositories. And then the website is available to use now for different research teams. And then this is all for us. Thank you for follow the presentation. Any question?
Could you tell us a little bit more about your team? Who's on your team, and how did you choose this project? Who did what part?
Yeah. Part of my team is Camila Garcia, that is here
Hi, nice to meet you. I'm here.
Yeah,
I'm
we are scientific lovers. Camila is a mechatronic engineer. I am a mechanical engineer. We are scientific lovers. We practice and uh, compete of different hackathons, Apple hackathons, NASA hackathons, different competitions around rocket prototype designs. And yeah, we love this astrophysics environment. And yeah, we are scientific lovers, and we have this time to attack this challenge and to try to do our best and attack these both prices to the best of use of data. Yeah, we just two scientific lovers.
I have one question. So
Yeah.
thank you for your presentation. I'm not engineering background, so I'm not confident that I can fully understand. But what is the future challenge to improve the accuracy more, for your model, or if you have anything? Yeah.
Yeah. We develop these both models with this people end that you can find on the application. But we have an first problem. The main problem is the time. You just have 1 day to train the models with a very big information, a big data. It's a very high problem. We just use around 100 of shadows data to train our model. This is because of the time, and but we can keep trying training or solution, and this a new iteration of hybrid model with AWS cloud data, where we can put a lot of different information on cloud, keep trying to ensure and improve our solution. The main trip of the process is the process of the data, client the curves, and we trained the deep learning with different libraries with TensorFlow and PyTorch, and we base our light GPM model, the machine learning model, with a paper that NASA gave us on the resources of the challenge. This is our main inspiration, right?
Thank you.
Right. And thank you. I think that's time. If we could go to the next person.
Thank you very much.
Thank you.
Team Helio Mesh is next.
Exactly. So my PC doesn't have a working camera, so I'll be using my phone. I don't know if you can actually see me right now. Okay. So let me just. Okay. So good afternoon, everyone. My name is Rui, and I'm in electrical engineering. And I'm excited to present you Willow Mesh, our project for these years, which is basically like this innovative hybrid satellite energy system. Well, in relation to our system, basically we try to combine both solar wind kinetic energy with conventional solar panels. We did this because we tried to create this robust hybrid power solution, which basically uses reinforcement learning to both forecast space weather and predict the best output control. And also this ensures reliable operation and prolonged mission durations, even in, for example, volatile space environment. So in relation to our prototype, we created this small video, which basically shows what we are trying to convey. Our prototype tries to feature like this modular solar sail setup that dynamically extends, as you can see in the video, extends and retracts the supporting poles. And everything is managed by the reinforcement learning algorithm, and it processes live data such as, for example, solar radiation and sail tension to fine-tune thrust and while maintaining structural integrity. For this, we used Omni2 dataset from NASA, which basically contains historical space weather insights, and it also helps us anticipate events like solar storms for proactive adaptations, for example. Also, this modular approach makes it possible to integrate this system into existing orbital satellites and satellites with different configurations and setups. In relation to the benefits, well, solar cells tries to revolutionize propulsion by using photomomentum from sunlight and delivering fuel-free thrust. There are some key advantages to this approach, which basically includes extended satellite longevity and also minimizes debris. It also reduces launch expenses and CO2 footprints through lighter designs, and this allows us to have clean energy backups for essential functions. And overall, this tries to foster sustainability and economical space exploration. Risks. Well, there are some potential risks with and challenges when it comes to solar cell systems like Iliomesh and first of all, for example, orbital crowding. Well, let's say that two satellites are not far away from each other. They could eventually collide in situations that they are not coordinated. We could also, for example, talk about light reflection towards Earth, which we could also face basically intense light reflections from this huge structure, the solar sail. And last but not least, interactions with solar plasma and magnetic fields are minimal in near Earth orbits, which could make eventually our solution not feasible. Well, going to the next slide, advancements. When it comes to advancements, we created a quick render, as you could see in the previous slide, to better demonstrate the concept behind our idea. And we also tried to create and start working on a reinforcement learning control system. However, I would say we were not that successful, but well, nevertheless, we still submitted the script to the GitHub repository in case you want to check it. Also, we thought about some features and ideas to enhance our project, and these include, for example, a SaaS AI platform that tries to process in real time magnetic field, solar wind, some other variables, for example, to optimize this control system. And we did also try to find some ways to minimize energy consumption, both by adjusting, for example, maneuvers and also orbital adjustments.
And sorry, I'm so sorry. It's about like 30 seconds left of the presentation.
Okay, great. We also thought about collaborating with CubeSat operators to start testing our system. So basically, in summary, Iliomesh tries to pave the way for resilient and eco-friendly space missions. Thank you.
This is awesome, Rui. I can start
Thank
with
you.
a question. If so, what aspects of this, Rui, have already been explored? What parts of this solution that you've proposed is net new?
Yeah, right. And we know that's why we try to come up with a different approach, and we try to also use let's say reinforcement learning and machine learning approaches to try and be a little different from the rest of the, let's say, the papers and the projects in the previous years. I don't know if that answers your question or not.
Not really. So, like, I was hoping that you could tell me, like, of the solution that you proposed,
Mhm.
1 and 2 have been explored, but the combination of 1, 2, 3 has never been explored before. That's what I was hoping.
Okay. To be honest, the technical details, I was not the one behind those technical details. It was just a colleague that was working on that. But yeah, unfortunately, she is not here with us. But yeah.
Can you tell us more about your team?
Okay, so basically everything related, for example, with 3D graphics and coding, I was the person who did that. Everything related to theoretical approaches, mathematical equations was Emin, which is actually the team leader. And for the rest of the team simply worked on the website and also on some posters and on these slides as well.
So, and what's the background of you and your team?
Okay, so I'm in electrical engineering. I'm currently pursuing a master's degree in robotics and automation. The rest of the team, I don't actually know their background, so I can speak for them.
Awesome. Thank you so much.
Thank you. I don't know if there are any other questions.
Yeah. What would your technology enable that can't be done today?
Yeah, basically, we tried to go for a modular approach, which basically could help us also implement this system in already in some satellites that are already in orbit, or some satellites that are not capable of using this technology, but with our system, since it's modular, we could try to implement in other satellites, in other configurations, in other setups. So I would say that's the main difference.
One last question. So, what do you think are the next steps, right? Like what does next steps for what you guys have already worked on look like?
I would say a simulation, because as you could see in that video, I mean it is kind of a simulation. It's not really simulated because we also used some kind of keyframed animations. But I would say that to really test and to prove that this system could work, we should try and go for a better simulator overall.
Awesome. Thank you so much.
Thank you.
Right, and I think that's about time. So we can now move
Thank you
on to
very
the
much.
next person. Thank you.
Thanks. Next up is Team Keynes.
Yep. Okay. All right. Can you guys see my screen?
Yep, looks good.
Okay. All right. So this is SHINES, the search for high inclination non-transiting exoplanet systems. So why do mutually inclined systems matter? Mutual inclination refers to the angle between the orbital planes of two or more planets in a system. In a typical planet formation scenario, it is expected that planets form in relatively flat coplanar disks. However, the presence of highly inclined system, or HINS for short, implies that the dynamics of planet formation are far more complex than previously thought. Finding them raises important questions about the stability of such systems over time and the processes that lead to the observed configurations. For instance, if planets can form in highly inclined configurations, this could suggest that the environment which they form in is more chaotic or influenced by external factors than the isolated disk model predicts. In fact, the recent discovery of KOI 134, a hint, has no known formation pathway, highlighting the importance of finding such systems to better understand them. So, how have we found them? Well, not really. But why? Well, the main issue is survey bias. Transits favor coplanar systems. In coplanar systems with low impact parameters, all planets will transit together. Yet it is predicted that 53% of systems have high mutual inclinations, meaning we'd expect hints across hundreds of known systems. But in reality, only a handful of confirmed systems exceed 10 degrees of mutual inclination. And as explained in the last slide, this observational gap is critical for formation theory, indicating we need additional mechanisms to explain planetary architecture diversity. So, what is our solution? Our solution combines two complementary datasets, transit timing variations and transit duration variations. These datasets will be obtained from the Kepler Space Telescope, and TTV and TDV data, in fact, already exists for many Kepler planets. TTVs measure when transits occur. They reveal gravitational interactions between planets and can detect non-transiting companions, allowing us to discover additional exoplanets in multi-planet systems. But the critical limitation is TTVs depend on only gravitational perturbations that affect the orbital period. These are largely insensitive to the viewing geometry. So TTVs data alone cannot constrain inclination. TDVs, on the other hand, measure how long transits last. And these are directly sensitive to orbital precession, making them a direct probe of mutual inclination, which is the key quantity that we're trying to constrain. However, while TDVs are known to be conclusive of mutual inclination, planets with TDV data are sparse, unlike the vast amounts of TTVs observed. So, how can we address this limitation?
We hypothesize that variations in transit timing and duration can be evidence of hints, or these high inclination non-transiting exoplanet companions. And we propose a model that can be capable of detecting these. So for this model, we have certain requirements. We need it to be adept at analyzing periodic time series data, and we need it to be capable of extracting features from our data through complex reasoning. Additionally, it must output a single probability value representing the probability that the system contains a hint. Next slide, please. So the model architecture that we settled upon has never been used before in exoplanet searching. We used a bidirectional LSTM encoder to provide the model with context. So this scans both ways to correlate data from both ends of a list using LSTM nodes. And bidirectionality here is very important because TTVs and TDVs are periodic measurements due to the orbital nature from which they arise. Also, we use a transformer, which performs feature extraction through self-attention. And finally, a multi-layer perceptron to convert the learning and analysis done by the transformer into the single probability value that we want, which represents if the system contains a hint or not. Next slide, please. This is just a diagram of our model. As you can see here, we included positional encoding and multi-pooling. Positional encoding just helps the transformer know the general layout of our data, the sequential nature. Next slide. And we also used a cross-entropy loss function to minimize confident wrong classifications. Also, we used the Atom W optimizer, and we performed hyperparameter searching on our 7-dimensional hyperparameter space. For time constraints, I'll skip over this as well. In terms of training and testing, we generated a simulated data set, more on that later, that we divided using the classic 80-10-10 train validation test split, and data was normalized by column. TTV data was normalized separately from TDV data.
As for simulating the data, we simulated the exoplanet systems using techniques from the Deep TTV and GRIT projects. Additionally, we've already simulated over 70,000 transits. Then, after this, we fit the center transit times and transit durations for every period. With this, we can then calculate the residuals, which are the TTVs and TDVs that we need to train them on. Additionally, we also encountered systems with both expected and unusual behavior during our simulations, as you can see below in the graph. In the future, our goal is to sufficiently train our model to identify all possible candidates and validate them before labeling them as hints. This helps expand the historically undersampled systems with high inclination. And once our model has identified possible candidates, we'll validate them through the processes below. You can find out more and explore our model directly on our website through this link. Through this website, you can also download the model for yourself to test and contribute any exoplanetary data you found by submitting it directly to our GitHub repository. Thank you for listening, and we'd be happy to answer any questions you have.
Very cool. Thank you. How did you come up with the idea of looking at the transit duration variations in combination with transit timing? Is that something that's been done before in the literature, or what made you think about that?
Yeah, so transit photometry, I've done a little bit of in the past with convolutional networks and such, and there's a lot of limitations on, the planetary diversity or the different planetary architectures that we can find. And so TTVs have been used for exoplanet detection since I think 2013, or maybe 2008 was when they were first theorized. But transit duration variations, so they basically first became indicative of possible mutual inclination in like early 2020, 2021-ish. But it's never been done through neural networks. So people have only, because of the sparse amount of TDV data that they have, it's not being used that much in like large learning models that like something that we're doing. And so if you kind of think about it like a transit duration variation, it causes something that's called secular nodal precession, which means that the orbital plane of the planets is going to slowly like precess over time because of like a highly inclined system. And so basically it's like a spinning top. And so as the orbital plane precesses, the projected inclination that we see will change. And so this changes, the transit cord length, which thus changes the duration. And so sometimes that can be hard to detect. So we wanted to also include TTV data in order to possibly find any correlation between TTVs and TDVs and inclination. Because if TTVs can somehow be correlated to the inclination of a system, that would pretty much revolutionize our ability in finding these high inclination systems, as currently the main limitation is just the lack of transit duration variation data that we have.
Just to add on to that, one thing Michael mentioned is the sparsity of TDV data. And that was really the reason why we decided to simulate data and look into that as well, is because right now, what we hypothesize is that the reason why we're not seeing these non-transiting companions that are at high inclinations might just be because we don't know what we're looking for. And so by simulating this wealth of data and training a complex model to be able to see these correlations, we're kind of taking a whole new approach on this idea of exoplanet identification. And yeah, that's sort of why we decided to simulate as well as use the model that we did.
Good idea. Thank you. Could you also tell us a little bit more about your team and how you came to this project?
Yeah. Okay, I guess I'll do it. So yeah, so we all met at the summer science program this summer in astrophysics, and we all really love astronomy. And this figured to be, we hung out a lot during SSP, learned a lot together. So we can continue it afterwards through this hackathon. And so yeah, we're all aspiring astronomers. I want to do exoplanet research in undergrad, and I want to do in general like observational astronomy. Joe, I know you want to do theory stuff, but
Yeah, Michael touched on it as well. Yeah, we're all super passionate about the field of astrophysics. Me personally, I'm really into transients. So I've done a lot with detecting peaks of transients, predicting them. And yeah, we all also come from like pretty solid programming backgrounds. So the work through this project was split fairly evenly. We all contributed to the model, to the simulation, um, and the website portion as well. So yeah.
And all of you is 3 team members?
Yes. Yeah.
Yeah, we're all seniors in high school as well.
Perfect. Thank you.
Just one thing one thing to add. We also had sources. We consulted quite a few research papers. So just wanted to make sure that those got up there for a little bit as well.
Right. Thank you. I think that's
Awesome.
time.
Thank you.
Thank you.
Awesome. Next up is Team Lumina. Behak, we lost your audio. I don't know if you can hear us, but I'm unable to hear you. No.
Hello.
Yes, now we can.
Okay. My name is Mehak, and my project is very simple. That is based on space weather impact of solar activities on Earth. I think I can share my slides.
Yes, please.
Okay. Okay.
We can see it.
Yes. My project was space weather impact of solar activities on Earth, and it's a simple yet interactive web experience that explains how solar and flares and space weather influence our Earth planet. And the idea was to transform the complex NASA's scientific concept into something visual and engaging. And the problem was the space weather is not just distant phenomena. Solar flares and storms can impact satellites, disrupt GPS navigations, and interfere with communications, and even damage our power grid on Earth. Many people don't realize that how strongly our space events are getting connected to our daily lives, and that's why I wanted to create a project that highlights these hidden connections. So my solution was that I code an interactive web page that visually demonstrates the solar flare activities and aurora's effects and impacts on technology and daily life, the impacts of storms and disruptions of GPS through by the space activities. Many people don't realize that how strongly space events are connected to our daily lives. That's why I wanted to create a project that highlights these hidden connections. And I use HTML, JavaScript, and CSS to make this project very easy to use, and anyone can run this project without any installing and some difficult or some powerful tools. And if we see that from the NASA's previous data, in which that in March 1989, a geometric storm triggered and caused a 9-hour blackout across the Quebec and Canada, and whole the province's power grids failed, and that's why I wanted to create this project, so everyone can be aware of the impacts of space on our Earth. And the technology and features that I used was the project was designed to educate and create awareness among students and teachers. And if we my front end is very lightweight and there's no installations, this all based on HTML and CSS JavaScript that we can run on our Chrome. And the visual effects I added like solar flares and auroras. Here I would like to like to show this. If you can see this my project, there's a demo for my project. Let me open this up.
Right, and sorry for the interruption. About 1 minute left.
No, I was trying to show my demo, but I think I couldn't connect it. Let me. Okay, we will move toward the next slides and why it matters. And the space weather is not just science. This project raises awareness in students, among teachers, or anyone interested in space, and can use it to understand NASA's space weather data in a fun or interactive way. It simplifies big scientific challenges into something that people can easily relate to, and how space weather affects technology and life on Earth. To build this project, I use web technologies like HTML, CSS, and JavaScript. I also refer to NASA's resources on solar flares and space weathers. I use some APIs from NASA's that used to present a graph from the previous global temperature change over the world. And my hope is that this project will inspire more people about space sciences and highlight why monitoring space weather is so important. So inclusion, solar flares and space weather explorer is about making science and more accessible. It's not just a project, it's a way to connect with people with invisible impacts of space, of weather, earth. And I would again try to present my demo of the project. Here you can see the demo of my project.
Meg, we can only see your PowerPoint, not the website. So you may have to reshare.
Okay.
We can see now.
And this is
We are not hearing any audio. If there's any audio.
Yeah. I mean, there's not any audio, just a visual website that shows how the space weather affects our Earth and global systems and our GPS and our daily life. Here is the data from previous past 5 years. I collected using NASA's API. That changes according to months, and temperature shows over the whole years. And at the end, I added some initiative for youth and students for the awareness to be a climate guardian, and they can plant trees and save energies and use these projects. So, is there any questions?
Hi, thank you so much for your presentation. Could you tell us a little bit about yourself and how you selected this project?
Yeah, my name is Mehak Shafiq, and I am a fifth semester bachelor's student, and I'm pursuing my IT degree. From this project, and how I came to the idea of this project is that I was just exploring some hackathons on NASA's and challenges. Actually, that's my very first project and my first hackathon I've joined. And when I'm exploring, then I saw a challenge that was to represent the space weather effects on our Earth. So I wanted to create something interesting and add some creativity. That's why I used only HTML and JavaScript, CSS to make it more easy to understand that how space weather impacts our Earth and our daily lives.
Thank you.
Any more questions?
So thank you for your presentation. Is very, how can I say, it's very visualized and easy to understand what is the problem of the space weather. And then what is the next option you want to add for this web page? Or for example, you can add some additional information, or you can create a movie or something, or if you have any idea, I'd like to know.
Yeah, there were a lot of ideas I wanted to add, but as I said, that was my very first project, and I have now some ideas that I wanted to contribute in future. That I will use some more data from NASA and add some more animations and animation movie to present that how our exactly the solar flares and global warming effects, and these our affects our daily lives in and interrupts our GPS and our navigation systems and our power grids, and how impact our ozone layers. And as you can see well in my demo, that when the ozone layer depletes, the whole earth can started to burn. And that and I have an idea to visualize that something into our daily lives, and add more animations, like if we plant more trees slowly, that effects will reduce and our earth will become normal.
Thank you.
Right, and I think that's about time.
Awesome. Thank you, Team Lumina. Next up is Team Bloombergs. We can't hear you if you're speaking. Okay, now yes.
Good. Wait a minute. Hi, we are the Bloombergs. Alpha, Jesse, Kayla, and Julian. Our team is made up of one middle schooler and three high schoolers, and this is our first time to our hackathon, and we are so excited. So let me hand over to Jesse to detail the project. So let's share.
So our project offers 4 different age groups, like the infants and toddlers, kids from 6th grade to 12, kids kids 6 years of old, kids 6-year-olds and 12-year-olds and teens, providing them with good illustrations of space weather and involving. It has good illustrations, like it has characters like Sunny and stuff, and good wording that kids, like young kids, would understand. We created a short story filled with colorful images and characters like Sunny that give good illustrations to kids. Uh, the story explains how the sun's activity can affect our daily lives, how making complex scientific ideas easy and enjoyable for kids to learn. We created another small story for the kids 6 to 12 years of old, 6 to 12 years, that have a good understanding about space weather than the infants. We created a short story designed for teens that explores space weather in greater depth, providing more detailed explanation about it, how it forms, how it affects us, Earth, and why understanding it is important for scientists, astronauts, and everyday people. We want this project to give kids in the world a clear understanding and engaging of space weather, what it is, how it works, and how it is, and how it affects people, animals, and technology on Earth and in space. Yeah. Now I'll pass it on to my partner, Alpha, to give a demonstration.
So this is the website that we created, and this is the introduction part. When you click on it, of course, it just brings the introduction, but then it has the age groups on top. if you want a story for an infant or a toddler, you could click on this and then scroll and go to the next page. And it will bring up a story of sunny space weather adventure, and it will explain, keep on. It will just keep on. The more you move the pages, the more the story keeps on being told. And if you want a story for kids 6 to 12, same thing, go back to introduction, scroll down, go to next page, and then it will bring up pages of another story for you, but with more detailed explanation, more than that of the infants and the toddlers. Then for teenagers, same thing, back to introduction. Then the next page, then it will bring up a story, but the story will have more detailed explanation than the other two age groups because this is a teenager who is interested in space and wants to understand it in more easier times. Yeah. And then the website also has a part of the data sources to show where we got from the data. And most of our data is from the NASA website. So that's our presentation. Any questions?
I can jump in. Good job. Thanks for presenting. What kind of APIs did you use? Can you share a little bit more in detail about that?
So the tools that we used are CSS, HTML, IntelliJ, and yeah, mostly those were the tools. We learned about them in class, but this was our first time using them, so we wanted to see how they work, the excellent job that they do. So yeah, the tools that we used.
Thank you.
Hi. I enjoyed telling us about some of the different stories that you developed. Could you tell us what led you to choose storytelling as your approach to address this problem?
We chose storytelling because it's like a creative way we thought we would approach this problem because very few kids know about solar and weather and all that, and many people want to know about it, but it's because of their age or it's because of the advanced words in which it's reported in, maybe the news or what, so they cannot understand whatever is going on. So we chose the storytelling in order to make them understand that information in an involving way and in an entertaining way.
Well, I think storytelling in science is incredibly important, and it's something that we often don't really think about, you know, till too late and sometimes. So thank you. I appreciate that.
Thank you. Any more questions?
So I have one question. Thank you so much for presentation, and was very uh, inspired that you have different stories for each of the generation, infants and the kids and teens, and it is a very good idea to tell the students. And I was wondering how long each of the stories you provide, like how many pages or like how big is it, that story? Yeah.
So it depends on the age group. So I think the bigger the age group, the more the ages, the more the pages. Because you can't make a 2-year-old to read 200 pages of science. Of course, they
Yeah.
won't be interested in it. So if it's like a 5-year-old, it will be like 6 pages, 4. It shouldn't be too much. Then for a teenager, should be some content because a teenager cannot read a book of just 6 pages. So
It depends on the weather.
Yeah, it
Okay.
depends on the age group.
Yeah. Understood. Thank you.
You're welcome.
All right. I think that's about time then. We could get to the next group. Thank you.
Thank you.
Thank you.
Next up is Team Hybrid Orbit. Team Hybrid Orbit, are you there? If they're not, we can always get back if they do come back. We have Team 6 Stars. Team 6 Stars. You all have submitted. Team 6 Stars. Going once, going twice, going 3 times. Next is Team Space Weather.
Space Weather. Space Weather made by Eita Miyagawa, Honoka Miyagawa, and Takei Minamizuki. We made digital picture book that about space weather and can understand for younger kids. Chapter 1. The Sun and Earth from on page 4. Chapter 2. Space weather and explain from page 5, page 6. Chapter 3. What space weather affects from page 7 to page 11. Chapter 4, what we learn from page 12. In chapter 5, the author's source questions from page 13. Glossary is page 14.
My name is Haludo, and I don't know much about space and space weather.
I'm space creature named Ipugao.
My name is Sakura. I'm very knowledgeable about space and space weather.
Earth is in solar system. Solar system has Mars, Mercury, and other planets. Those planets moving around the sun.
The sun and solar system are in space. Space is created by the Big Bang.
What is space weather?
Space weather is a solar activity like solar flare, coronal mass action, CME, solar winds that will be phenomenon where the space environment on Earth.
What is relationship between a sun, Earth, and space weather?
Space weather has various impacts on activities on Earth, while the sun's UV rays and space weather falls threats to Earth, damaging system and destroying our technology. But life on Earth wouldn't be possible.
Space weather affect many things such as people, farmers, and pilots.
The solar system is sudden explosion of particle energy and magnetic fields and material blasted into the solar system by the sun. The effect of space weather on people caused a large-scale communication outage, large-scale power outage in variable regions, people or airplanes as the moment may be exposed to radiation.
Measure people can take against the effect caused space weather and what is needed for this measure. Preparing emergency food and water for long power outage, securing multiple means of communication, regularly checking space weather forecast.
The effect of space weather on farmers and pilots. Farmers effect. The vegetable harvesting tractor stops working. Pilots effect. Even at cruising altitude, aircraft passengers and pilots serve radiation exposure from space.
Countermeasure against the effects of space weather on farm workers and pilots, and what is needed for those measures. Preparedness for infrastructure description of fuel mitigation of vulnerabilities. Pilot temporarily suspend communication, broadcasting, and transportation flights operation on a permanent basis.
Right. And sorry for the interruption. About 1 minute left.
Now let's take another look at the slides we've gone this way to see together. Space weather is solar activity like solar flare.
There are some living systems and whistleblowing or technology. The sun is indispensable. Without it, life on the Earth wouldn't be possible.
Space weather affect to many things like people, farmer, pilot, and other. That's it. Thank you for watching our slideshow. We have a glossary and author thought after this slideshow.
That also source impressions. As I wrote this picture book, I kept in mind how accessible it would be for children to read.
I didn't know about space weather, but I learned this.
Across this study, I highlight the importance of space weather.
Thank you
for watching our slideshow. That's it. We finished.
Over to the judges.
Wow, that was great. I have a question about, so first of all, could you remind me the name of the alien?
His name is Ipugo.
I think it was on like the first slide or second slide. And Ipuga, okay, Ipuga wa kawaii desu ne. I really like all the graphics, and I'm wondering, how did you create the graphics for your story?
We made that picture the
We made picture from some of AI and some of used from the free image site.
I think you did a really good job, combining and selecting them, and it was a fun way to tell the story. Thank you.
Thank you.
Thank you.
Thank you.
I have one question. So, first of all, thank you for your presentation, and it was amazing, and you did a good job. And then I know this illustration, where this illustration came from. It is very typical Japanese free illustration, site, and I know it's very well. And then, so I was wondering, who will be the target for your project for to read, like I think it's for the kids or the teenager or the who are you intend to
Uh, like
retargeting the younger kids to the older person, so we want to be like any person can read this book and getting interest uh for the space weather.
Great, thank you so much.
If there are no more questions, last up is Team Honolulu. Team Honolulu, we have Joy and Divine who were talking to me earlier.
They're going to join.
Okay. Do we also have 6 stars in the room?
Hello, are you calling on Honolulu or are you calling on Six Stars?
Honolulu, actually.
All right. Um, can we share our screen?
Yes.
Okay. Wait, can you see our screen?
We can.
Okay.
This is the meet. I'm Divine Chivazo, and this is the Meteor Madness Challenge. And this is an in-depth look at NASA's Meteor Madness Challenge and astroanalysis. This is the introduction. The NASA Metro Madness Challenge invites participants to design a simulation that tracks meteor and their trajectories, enhancing understanding of the impacts of meteors if they were to hit Earth. This initiative fosters innovation in a space exploration, aiming to develop an interactive visualization and a simulation tool that uses real data to help users model asteroid impact scenarios, predict consequences, and evaluate potential mitigation strategies. Asteroid 2025 QY1. This asteroid has city destroying potential, could release energy similar to a nuclear bomb, creating firestorms and shockwaves. Asteroid Apophis. This asteroid would devastate a region or ocean, generating tsunamis and massive atmospheric effects. No global extinction, but catastrophic regionally. This asteroid, 2025 RL8, likely to burn up in the atmosphere or cause small local bursts. Asteroid SQ12. This asteroid could cause regional destruction with blast waves, fire, and small tsunamis, not globally catastrophic. This is the asteroid composition. A rocky context, metallic core, irregular shape, ice and rock mix. This was our coding techniques. We used HTML, CSS, and Java language to put together a design. The challenges that we faced was that some of them being obtaining right data for the meteors. Instead, we decided to substitute the data for meteors that would with data for asteroids. Another challenge we faced was debugging certain aspects and adding a 3D model OS Apophis with AI. This was our conclusion. Through the challenge, many can be educated on meteors. This challenge brought fun, innovative, and productivity to our team. Coding while learning more about NASA, meteors, and asteroids brought us valuable experiences and piqued our interest in astronomy.
Okay. Hi, my name's Joy Deborah, and I'm going to talk about our, I'm going to talk about, I'm going to present our actual project, the visual project that we created. So this is our project, and we wanted to create a visual representation of the meteors and put together their information. So we wanted to come with a modern friendly 3D gallery design. So we created this. You can click on the cubes and it will show you the asteroid's stats, the size, speed, how close it is to the Earth, or like the time it would hit and impact the Earth, the region of impact, and what would happen after the impact. This cube was supposed to show the 3D model of the asteroid in the middle, but we faced challenges putting the asteroid in the middle. We can also click over here to see the mitigation strategies of the asteroids, and it allows us to see what we can do to lessen or to monitor the asteroids. Okay. Thank you. Any questions?
I can go in. Firstly, great job with the website. What was your inspiration for picking this particular problem? Or and so it's two-part questions. One is your inspiration, and two, like what platform do you use to design your web page?
My inspiration for creating this was when I read our inspiration was when I read the prompt for the Meteor Madness. It explained that we had to use visual design, and I recently learned about web design last year, so I was really excited to use it. And I loved art too. So taking this opportunity, I was able to create a 3D gallery. And yeah,
What do you think would be the next steps in your project if you were going to continue it?
I would try and add the 3D models of the asteroids, or if because we substituted the asteroids for the meteors, we would take more time to find more information on the meteors and substitute it for the asteroids information. But we would definitely try and add the 3D models to the cubes and more information too.
Thank you.
Thank you. You're welcome. Are there any more questions?
I have one question. Sorry if I miss any your explanation, but why did you pick up those asteroids you showed, like 8 or 9? I saw. So what?
Because
Yeah.
I went on the Eyes on Asteroids page for the NASA thing, and I picked out a few asteroids that I saw. So it was there. Those four were just some of the first four that I found.
Okay, and then can you add this additional one if you a new one were
Yes.
found?
Yes, I can.
That's good.
Any more questions? All right, thank you.
Wow,
Thank you.
that was awesome. I think, needless to say, this was an amazing set of presentations from 10 different teams. We are still missing Team Six Stars. I don't see them on Zoom, any of the team members. So I'm assuming that they are not going to present today. And so that being said, we had 10 teams that presented, and what an inspirational journey it has been so far. Awesome job, everyone. If you haven't yet, and by the way, if this is the last call, if you haven't, if presented and you do want to present, please unmute yourself and
Hello, hello.
hello.
Yeah, we're here.
Oh, are you Team Six Stars?
Sorry, I forgot to change the name. We lost a member.
Okay. Oh, okay, cool. So if you can present, that'll be amazing. Very good.
So, my name's Enoch,
And my name is Naomi.
and we are gonna present Will Rain on My Parade. Uh, can you see my screen?
Yes.
Yep.
Hello, everybody, and welcome to our presentation, Will It Rain on My Parade? We're going to go over our table of contents, which include all about us, introduction to this challenge, our inspiration, the point of all of this, problems we encountered, and our conclusion. All about us. We are a group of 5 high school students, and together we had different roles to fulfill one common goal. Introduction to this challenge. The challenge we chose, Will It Rain on My Parade? This challenge required us to develop an app using NASA Earth data that lets users create a personalized dashboard to view the likelihood of chosen weather conditions at a selected location and time. The picture in the middle is the omega block pattern, which means that the weather is stuck in one place, which means it's either warm or dry in one place and stormy and cool in another. From this, we learned the importance of experiencing life with others, connecting with others, how to focus and analyze the effects of events, how to brainstorm ideas effectively, and that while we cannot control the weather, we can plan ahead.
This is our rough draft of work, the code and everything behind it, how we did it, what to do to make it. And this is the final product. You scan this QR code, it goes to the app and shows you how the weather, you type in the city or the town, it does all that. This is how it looks like over here. Our inspiration. In the beginning, we were inspired by a simple desire to create something meaningful out of everyday experiences. The small moments, challenges, and even setbacks sparked our curiosity and fueled our drive to explore new ideas. The starting point reminded us inspiration often begins with ordinary before it grows up to something great. What's the point? The point, this project has shown us the importance of new beginnings and experience life fully. It emphasized the life value, connecting meaningful with others. We learned the power engaging in our brainstorming to share ideas, and it encouraged us to reflect on not only events themselves, but also on the effects those events can have on people and outcomes.
By focusing and analyzing and stepping back, we gained a better understanding of the bigger picture. We realized that while many things in life, such as the rain, cannot be controlled, we do have the ability to prepare, anticipate, and plan ahead. This experience reminded us that success often depends on not controlling every circumstance, but on building awareness and foresight. We learned that thoughtful responses to challenges are often more effective than attempting to control the uncontrollable. Problems we encountered. First, we started off at 6, but now we are 5. We're barely able to meet up in person, and even when we're able to call, it's for at most an hour. And we couldn't really call that much because we had much other work to do. Conclusion.
This project made us think about life and often those challenges when we expect the least of them. But instead, letting those moments stop us and it reminded us that we can choose to keep going, find our strength, learning, embrace our struggles that push each other to go far, limits succeeding our ideals. Thank you for listening.
Thank you for listening. Any questions?
Thank you. I was wondering if you could tell us a little bit more about your app that you created and how somebody might use it. Similar or different than like an existing weather app we might have.
Someone might use that app by like simply just go on their phone and download the app, open it up, and the reason why it's different than the rest because it's like it's more adaptable and easier, and it shows you it changes by the second. Other weather apps change by like the day, but usually ours changes by every single second. The weather changes. It goes from satellites and everything, and yeah.
What's it called? Also, in our weather app, it updates by the second. You can choose to update it whenever. And it's kind of like other weather apps, but like it's like better. It's more efficient. It like even shows like the rain coverage in like a certain area. That's why we decided to make it want to be different.
So what I heard is it's like real time and maybe it's more local. Is that what you're saying? Is it's like hyper localized?
Yeah.
Yes.
Okay. And then I also just wanted to say this is a comment. You made this statement, thoughtful responses are often more useful than attempting to control. And I thought that was a really great insight. And I also appreciate your other comments that you shared. Thank you.
Thank you.
Thank you.
If you want, we can go back to the slide so you can use a QR code to scan on the phone and download it.
Sure.
It's about a minute for it to fully download and get all the steps, but it'll be there. Is there any other questions about people scan the QR code?
Awesome job. Awesome job. 6 star, now 5 star. Very, very good. And hopefully you get the 5 stars on the App Store as well.
Thank you. Thank you.
Very cool. Very cool. I'm glad we all made it. There have been 11 amazing presentations so far. And I think I'm going to take over your share 5 star for a minute. I think if people have done scanning the QR code, if not, you can also reach out to the teams or reach out to us. We have the presentations. We can give you the QR code at that time. All right. Awesome. Thank you. Wonderful. So what's up next? The judges have a very tough job in front of them, and I'm hoping we'll all give them some time. So the judges will take around 30 minutes to determine the winners. We'll have a breakout room where they can deliberate and come back with the winners. However, as I had said earlier when we opened up, you've experienced this hackathon now, whether you're a first timer or whether you've been a repeat participant, and we've got a heady mix of both. You've experienced this and you've come across whatever was good, whatever we can do better. So if you can please fill out this survey, it'll really help us understand how to do better going forward. So there's a survey. The first one is the form that if you can fill out, it will be really amazing because we'll understand how to do better next time. The second one is the Global Satisfaction Survey, and that's the survey from our global organizing team for them to understand how to make the NASA hackathon better going forward. So if you can fill this out in the next 30 minutes while the judges are deliberating, that will be amazing. Eriko, I'm going to hand over the host control to you if I can just figure out how
I
to do
cannot
that.
somehow post a chat message in here. So.
Okay. All right. I'm going to make you the host.
Okay. You can stop sharing so that you can share the same thing.
Yeah.
Okay, it's in 30 minutes. Everybody, please come back in 30 minutes, which is 3:50 in Eastern.
Cool. The survey links are on the Zoom chat as well as on Discord. So if you're in Discord, please go there. You'll find both the link to both surveys. And thank you in advance for filling those out.
Cause you're a sky full of stars. I'm gonna give you my heart. Cause you're a sky full of stars. Cause you light